Hello, I'm Dr. Paul Behum from the Office of Surface Mining. I want to thank the organizers for inviting us to present at this meeting. Today I would like to discuss our assistance efforts related to the occurrences of artesian net acid discharges in the Western Interior coal field. We will then discuss using the experiences gained in this remediation to treat additional sites. In this presentation, I will briefly discuss the geologic setting of artesian coal mine discharges in western U.S. I will also provide an overview of the passive treatment technologies applicable to these artesian discharges, which are in most cases net acidic. The West Interior Coal Region is an area of predominantly bituminous coal that lies west of the Mississippi River and east of the Great Plains. The Illinois and Michigan coal basins lie to the east, and the Gulf Coast province, an area of low-ranked lignite coal, lies to the south. Historically, most of the mining in this coal field has occurred before the Great Depression. This paper will concentrate on AMD abatement within an area of folded and faulted strata known as the Arkoma Basin. This coal basin is largely known as a natural gas production area. The principal coal bed mined in this area is the Hartshorn coal bed. The Hartshorn Formation crops out within the Arkoma Basin as shown in this map to the right. Artesian discharges within the Arkoma Basin can get categorized into two groups, those with low flow rate and those with higher flow discharges. The low flow discharges typically have low to moderate net acidity and low aluminum content. These include the LaBosque, Rock Island No. 7, Jeffries Discharge in Oklahoma, and the No. 6 mine discharge in Arkansas. The Rock Island No. 7 and Jeffries discharges emanate from mine pools deep within the Hartshorn Basin and are characterized by much greater iron and sulfate levels. Several discharges in the basin have similar water quality but much greater flow rate. These include the Hartford discharge in Arkansas and the Stacy and Gowan Mine 40 discharges in Oklahoma. We will concentrate on the LaBosque discharge, the Hartford discharge, and the Stacy discharge in this discussion. The Arkoma Basin discharges are shown here, some of them. The Stacy discharge we'll be discussing is on top here, and you see down below two wet seals constructed for the Jeffries Field and Gowan Mine 40 discharges. Over here on the left, you can see the nearly completed 2005 construction of the Rock Island No. 7 discharge in Hartshorn, Oklahoma. On the Arkansas side, the Hartford shaft discharge can be seen here prior to treatment, and then after treatment, the discharge from two vertical flow ponds is shown. On the left side, we see the discharges from the Arkansas No. 6 mine discharge. So the LaBosque passive treatment system is a case example of the low flow, moderate acidity, and low aluminum type discharge. It employs simple passive treatment technology, anoxic limestone drain, oxidation pond, and aerobic wetland. This type technologies are characterized by lower operation life, less maintenance, and low installation and operating cost. Looking at the baseline data at this site, we see that the iron levels are relatively moderate, and there's low aluminum sulfate. The discharge itself occurs in the valley next to a long ridge known as Bull Hill. At the outcrop of the Hartshorn coal bed occurs near the crest of this hill, and the coal bed then is mined down dip into the valley floor. In the bottom of the valley floor, the lowest level of the workings was an artesian well, which was initially a dewatering well for the mine. This slide shows a typical design performance chart that is used to guide treatment specialists on the techniques used for passive treatment of acid mine drainage. The water at the LaBasse system is net acidic, so we need to use the right-hand side of this chart. And with iron levels being over 20 milligrams per liter, we have two options: an anoxic limestone drain and a vertical flow pond. Because the aluminum level at this site is low, the best solution is to use an anoxic limestone drain. And then we use, with a low acidity, we're able then strictly to use oxidation ponds and wetlands to precipitate metals. OSM assisted in the initial design by coming up with a conceptual design for treatment and provided this information to the Oklahoma Conservation Commission, OCC, that ended up completing the construction of the LaBasse system. Here we see the anoxic limestone drain, oxidation pond, and wetlands in our conceptual drawing. The system was constructed in 2003 and 2004. The anoxic limestone drain then appears as a long linear trench filled with limestone with plastic wrapped like a burrito to seal out oxygen. The discharge pipe, the inlet water comes in from the captured upwelling at the mine seal down and through the ALD and discharging into an oxidation pond for oxidizing metals. Here we see the discharge pipe from the ALD after construction, and then soon after construction, the wetland before the plants were emerged. Alkalinity is produced in two ways within an ALD. Due to the lower pH, there's some dissolution of limestone, which is calcium carbonate, with the hydrogen ions from the low pH waters. The produced then is the bicarbonate ion, and the bicarbonate ion is the principal source of alkalinity from this passive treatment technology. Alternatively, however, this dissolution of limestone is supercharged because calcium carbonate also forms, along with the hydrogen ion interaction, carbonic acid within the closed system of an ALD. The carbonic acid then also dissolves additional calcium carbonate and produces additional bicarbonate, enhancing the alkalinity generation within the ALD. This third reaction here, where calcium carbonate is dissolved by water, is relatively insignificant. So looking at the baseline water quality of the system, and we see that it's pretty similar to the long-term measurements from 2003 to 2021, the performance measurements of the LaBasse system. We see there's about 38 milligrams per liter iron passes through the ALD, but the alkalinity is greatly enhanced up to 152 milligrams per liter on average throughout the life of the system. Then the iron is allowed to quickly precipitate at this low pH buffered water and down to low levels. And that's the principal goal of our treatment system. Here's a chart showing the rapid decrease of iron levels at the oxidation pond discharge. Polishing again with the follow-up oxidation pond wetlands system. Thank you. The high flow, low to moderate acidity and aluminum regime is also treated by several systems within the Arkoma Basin. The one I'd like to discuss further is the Hartford PTS in Arkansas. We see that that is treated by three technologies: vertical flow ponds, oxidation ponds, and aerobic wetlands. This system is characterized by a shorter operational life, more maintenance due to the high flow rates, heavy metal loading, and the higher initial construction cost and operational cost. The Hartford system is located across the Arkansas border in the small Hartford-Huntington coal field. in Sebastian County. AMD is again due to upwelling water, in this case from a large air shaft from the Hartshorn coal bed. We see here at the top the initial wetlands mine discharge area that was created prior to construction. The shaft is actually located here in this clump of pine trees prior to construction. Post-closure, the mine pool discharges this high flow water with low pH and high iron concentration. Between 2009 and 2013, OSM, along with the Arkansas AML program, conducted a baseline study at the Hartford Passive Treatment System. Median pH was found around 4, but very high flow, 400 gallons per minute at times during the wet season. Iron levels were also elevated along with aluminum and manganese and sulfate. This produced net acidic discharge once again. Looking at our design chart then, where does this water fit in? Once again, net acidic water, so it's on the right-hand side here, and with the iron levels greater than 20, the two alternatives are noxic limestone drain or a vertical flow pond. With the aluminum being well above 1.5 milligrams per liter, then vertical flow pond was the technology of choice. Once again, this would be followed by oxidation ponds and wetlands to precipitate iron. Arkansas AML program designed this large treatment system to treat the Hartford discharge. A concrete collar was constructed around the former air shaft location to channel the water to 4 oxidation ponds. These operate at low pH conditions, unlike the number 6 site where we are able to construct a vertical ALD within the air shaft prior to treatment in the oxidation ponds. Those oxidation pond discharge then discharges that low pH water to 2 vertical flow ponds, one to the north and one to the south, which in turn bump out the alkalinity and precipitate the final amount of iron within the follow-up aerobic cell. This view here shows the concrete-lined oxidation ponds at the shaft discharge, followed then by the final oxidation pond, which is receiving discharge from the vertical flow ponds. Looking at the performance data for this system that was constructed in 2014, we see that the long-term water quality was very similar to the baseline, and that iron is pretty much is removed by that initial oxidation pond, large amounts of the iron. This was a little bit unanticipated that the low pH oxidation would be so aggressively remove iron. It also removes some of the aluminum, surprisingly. Alkalinity boost of over 170 milligrams per liter is produced in the 2 vertical flow ponds. The follow-up oxidation pond then removes and polishes the remaining of the iron and aluminum. Manganese in the system is not removed to any great detail due to the technologies employed. Here we see that in these charts that the flow through the vertical flow ponds is uneven due to partial plugging of one of the vertical VFPs. This other chart shows that there's a large increase in the pH in the vertical flow ponds, and then being well buffered is maintained throughout the discharge. Here we see in the orange chart that the iron is quickly removed by the oxidation pond, initial oxidation pond, and then polished to near zero in the discharge. The calcium level is greatly increased in the vertical flow ponds, and that's parallel with the dissolution of the limestone and production of alkalinity. Aluminum is quickly removed in the oxidation pond and then the vertical flow ponds, and manganese passes through the system as discussed. So what have we learned and how can we apply that to other systems? So this is the large discharge from our Artesian well at the Stacy discharge near Howe, Oklahoma. Looking at this site, you'll see there's a series of coal mines that crop out just southwest of Howe, and one of the largest being the discharge from the at the Stacy property. So a general solution on how we treat this water and how to come up with a remediation plan is to obtain right of entry from the private loan owner, to complete a topographic and baseline hydrologic study, to complete a series of jar tests to evaluate the ability of local limestone to produce alkalinity, conduct geochemical modeling to evaluate the chemistry of the water, and then to develop a conceptual passive treatment design, and finally to construct this treatment system. So this is some of the initial reconnaissance data prior to really conducting any formal hydrologic investigation. And we see that the pH is around 4.5 in this discharge, relatively moderate iron levels of 39 milligrams per liter, but aluminum content is close to 3 milligrams per liter, which is problematic for an ALD. So then looking at this design chart again, so where do we fit in? We have to go again, net acidic water to the right-hand side here. We're looking at waters over 20 milligrams per liter, and with the high aluminum content, it's difficult to use the ALD technology. And once again, a vertical flow pond would be similar to the Hartford system, would be the technology of choice. Running this quickly through AMD Treat software, OSM's software program, we are able to see that just the cells themselves can be treated for a relatively low amount of $600,000 for this large flow discharge. Additional costs would have to be incurred for constructing access roads and drainage ditches. I'd like to acknowledge the assistance that the state agencies that we cooperated in our studies, Mr. Kevin White, the manager for the Arkansas program, two retired mining specialists, Charles McCool and Wayne Van Buren. In Oklahoma, the former Conservation Commission staff that helped us was Henry Roy and Mike Sharp. And then my colleagues from the Office of Surface Mining. There are too many to mention, but I'd like to point out the work from Lachelle Harris and Brian Hicks. And that's it. Thank you. I'll hang around for comments.